Okay, we're now going to look at angular displacement theta. What is it? Well, it's simply a measurement of angle. Here is the defining equation. So it's a ratio of arc length S to radius R. Now, 1 radian is defined as the angle swept through by by an arc length S, which is equal in magnitude to the radius R. So if S equals R, we have swept through 1 radian. Another example, which is quite useful, is to consider 1 whole revolution, where we've gone through a circumference for the arc length. We know that's equal to 2 pi r. Or 1 revolution equals 2 pi radians. Saying this is useful to compare degrees in radians if you want to convert from one to the other. So we know 360 degrees is 1 revolution, and that's the same as 2 pi radians, therefore. Using that, you should be able to convert 30 degrees into radians, and if you're successful, you should be getting 0.52 radians. 200 degrees should be giving you 3.49 radians, and 5 revolutions should equal 31.4 radians. So have a go. Okay, we're going to now look at another concept that is angular in nature, that is angular velocity. Well, starting with angular speed, it's just simply the angle swept by the radius per second when tracing out a circle. Angular velocity is the same thing but with a given direction. Example, clockwise or anti-clockwise. Here's the defining equation. Omega equals delta theta over delta t, which is the rate of change of angular displacement. The units are radians per second, usually written like this. Okay, example. A wheel spinning 10 revolutions in 20 seconds would be moving an angular displacement of 20 pi radians, because it's 10 revolutions times 2 pi radians, so 20 pi radians, and the time would be 20 seconds. So the two 20s cancel out, leaving us with pi radians per second, which can be written to 3 decimal figures as, or 3 significant figures, I should say, 3.14 radians per second. Another concept that's quite useful to consider is the linear velocity of a point that's moving in a circle, and to arrive an equation for that is the next note here, starting with this idea of instantaneous angular velocity. That is the angular velocity at one moment in time. That's what the word instantaneous means. We find that by considering the differentiation of angular displacement with respect to time, d theta dt. And now we're going to substitute that in a bit later. If we start with this equation, which is the relationship we just saw before, the arc length S is equal to the radius times the displacement, the angular displacement theta. If we differentiate both sides with respect to time, we get ds by dt on the left hand side as equal to dr theta by dt on the right hand side. Now we just have introduced this concept before. We can substitute that in, move the radius out to the front because that's a constant, and before you know it, we've derived this equation here, which relates the linear velocity v to the angular velocity omega. Here's another example. A ceiling fan of diameter 1.6 meters rotates at 90 revolutions per minute. What is the velocity of a point on the tip of the blade? The first step in solving this question is to change the 90 RPM into radians per second. This is an angular frequency omega in disguise. So once you've converted that into the appropriate unit, radians per second, it's a simple matter of multiplying it by the 1.6 meters to find the linear speed v, which should turn out to be 7.54 meters per second. So have a go. Once you've converted that and multiply it by 1.6, you should be able to get this number in meters per second. Next, we're going to look at period and frequency. Period and frequency. So period capital T is the time taken for one revolution. Now, since omega is the change of angular displacement with change of time, for one entire revolution, that's one oscillation or one complete revolution, that's 2 pi radians of displacement. We can put that in and call time capital T, because that's the time by definition we're talking about. So there's our simple equation relating the period T to angular frequency or angular velocity, is what we call it so far. Why do we call it angular frequency sometimes? Well, here's why. We know that the linear frequency F is 1 upon T, so the inverse of this equation here is this one here. So omega equals 2 pi F, and this is why we call omega angular frequency, because it is directly related to linear frequency by this equation. So here's an example you can try and solve using that equation. A mass on the end of a string is whirled in a horizontal circle. It makes 8 full revolutions in 5 seconds. What is the period, frequency and angular frequency for the motion? Well, simply taking 5 seconds and dividing it by 8, you get 0.625 seconds for the period, time for one revolution. And you take the inverse of this number, 1 over 0.625, you should get 1.6 as your answer there, per seconds or hertz. And then multiplying the 1.6 by 2 pi, which is applying the 2 pi f formula, we should be able to find omega as equal to 10.1 radians per second. But have a go with your calculator to make sure you understand. Now we'll look at another way of thinking of speed in a circular motion. We consider a mass moving in a uniform circular motion. It travels 2 pi r, which is the circumference, in a time capital T. So distance over time is simply 2 pi r over capital T. So there's a nice little equation that relates linear speed, radius, and the period. A similar vein, centripetal acceleration and force can be reconsidered. The equations can be reformulated using omega, the angular frequency. Since we know this equation, we derived it before as v squared upon r for the acceleration. And we also know v, the linear speed, is r, the radius, times the angular frequency. If we substitute that into there, we get this. If we square it and sort of cancel out some r's, we get this equation here. So that is a very useful equation sometimes when you're in a hurry to find acceleration and you've just got the angular frequency. Multiplying that by mass, of course, will give us the force, the centripetal force equation, mr omega squared, which again is useful depending on the information given in a question. So one final example. A drum on a spin dryer has a radius of 28 centimeters and it rotates at 60 revolutions per minute. For a point on the edge of the drum, calculate the centripetal acceleration. First step then is to convert this 60 RPM, which is revolutions per minute, a frequency, into revolutions per second. That would give us linear f here. We multiply it by 2 pi and we'd get omega in terms of radians per second. And once we have that, we can plug it into this equation for the acceleration and solve by multiplying by 0.28, being careful to change the 28 centimeters into meters. You should get this answer here, so have a go.